Good. Just started recording the screen because I said this will be part of the initiative I'm doing. So,
Sure.
yeah, so I guess I'll have to introduce the sort of theme and you, and then we can get started.
Okay. What's this for? Just out of curiosity. Is this like you're just asking questions to learn, or is it you're gonna record this and show it on YouTube, or
Yeah,
all
I
of it's
was,
fine with me. I'm just curious.
yeah, I was actually planning on recording this and showing it on YouTube, but not my own YouTube. It's associated with the startup.
Okay. Yeah, that's
So,
fine.
So I can introduce like what this is and then I'll introduce you. So
Okay.
I'm currently collaborating with alumni from MIT's Julia Lab, and so they graduated and they've started this EdTech AI focused startup called Visuara AI Labs. And we realized that we had similar interests, so we just started collaborating, and I'm kind of doing my own thing, but it fits their bill. So it's like great, you just do your thing and sort of will sort of like they get derive benefit from that. So they're focused on like creating educational content for scientific machine learning and help like make people aware about the field, help them out with research projects, um, and they want to uh, expand to like develop in-house research capabilities. So as part of that broader scientific machine learning initiative, I thought it would be a good idea to actually interview prominent scientists who are doing that sort of thing, because it's a very broad field and it's very hard to define what that really means. So
Mhm.
I sort of just reach out to scientists who've done interesting work, and it's an opportunity for me to learn from them and also to like create awareness so that more people know about the intersection of science, or mainly physics and like machine learning.
Mhm.
And you've
Sure.
done like really cool work in that space, and then you have your course, the link you sent me last year, like machine learning and optics. So and then I
Yeah.
read your paper like CNNs teach microscopes how to image and the
Mhm.
physical layers and stuff. Um, so that's why, and then my whole main research project just never went anywhere. Um, like it was sort of, I couldn't really follow my interests. So with the startups, with what the startup is doing, I can. And then I thought, wow, this is like a great opportunity to actually reach out and talk to you if possible. Because if my internal research goes nowhere, I can't reach out again saying, hey, I've done this and do you have any like opinions on this, right? So I thought,
Mhm.
well, this is lining up. Maybe I can reach out to you with this.
Sure. Yeah.
Okay. So first, I think I'll have to introduce you for the channel, and then we'll get into the questions. So
Sure.
you're Professor Ulrich Hostmeyer at Duke. You're an assistant professor at Duke in the biomedical engineering department, and you're
Mhm.
an optics genius who did his PhD at Caltech with in Chang Hui Yang's group,
Mhm.
and then you did your MS from MIT's Media Lab, and you did your
Yep.
BS at Duke, your current university, in physics, and you minored in Japanese or something like that.
Yeah. Majored in Japanese. Yeah.
Oh wow!
That's
So
yeah.
majored in physics and Japanese,
Yeah.
and you
That's
also
right.
run your own company, right? Ramona Optics.
Yeah, I'm a co-founder of Ramona Optics. I don't run it, but I help and work there sometimes a little bit. Yeah.
And you also teach this course on optics plus ML and do work with physical layers. Yeah.
Yes, exactly. Yep, that's
Yeah.
right.
Yeah. So I
Yeah.
think that's like your introduction. And this is just the second episode. So you're the second guest. And
Okay.
I like to sort of keep the talk and the introductions very informal. So I go to research seminars where they're reading off like he did his PhD here and his postdoc here. And I just don't like that because it's not organic, and it means that like the host isn't really passionate or invested in like the guest. They're not like, oh, this guest is cool. It's like, why do you have to read off a script? So I try and not have, so I do have some questions prepared, but I'll try and not look at it because it's more like I have things I want to ask you and it'll be great to learn from you. Sorry.
Sure.
So
Yeah.
you're a physical scientist who got into machine learning and primarily you did optics, right? So
Yeah.
I'd love to know more about your life and career journey. So where were you born? Where did you grow up? Why physics and Japanese? And how did you get married to optics and then cheat on it with machine learning? The whole story. And
Sure.
getting
Yeah.
into startups and your experience at grad school and Duke, and yeah, I'd like to know the whole story.
Sure. That's a lot of questions. But I'll try my best. So I grew up in the Bay Area in Palo Alto, California. I was always interested in science and math, and so I had some nice opportunities to work on some research projects when I was a undergraduate here at Duke. And I worked a bit on astronomy type stuff. I got really interested in how telescopes work. I worked a little bit on some neutrino detection type stuff, and I got interested in how that whole apparatus worked. And so I kind of learned that I was interested in how devices were made to measure things, which led me to start working with a former professor here who's now at the University of Arizona, David Brady, who worked on cameras and really neat imaging systems, and that kind of spawned my interest in imaging and all of these interesting computational methods to process images. Um, and so that, eventually led me to grad school on that topic. And then in grad school, I became interested in microscopes because they're just a lot more fun to play with. There's a lot more you can do. You have full control over everything, the illumination, how the sample is prepared, everything else you might need to get the data you want to see. And so that was always exciting to me, and I enjoyed that uh, aspect of it. And so I kind of focused more and more on microscopes as the years went along. And then in graduate school as well, both in my master's degree, but then more so in my PhD degree, I got interested in machine learning methods. At that time, neural networks was kind of like a bad word almost. They were something that had been attempted in the early 90s with a lot of fanfare and excitement and had completely fallen out of favor, essentially. Not many people were working on them or studying them. This is in 2009 and 10. And I just more from a mathematical perspective was interested in how machine learning worked, and the history behind it, and kind of all of the findings that led to the ability to create classifiers and stuff. And so I took a course at Caltech about that by a professor named Yasser Al Mustafa, something like that. I forget the full
Yeah,
name,
he
but
has
it
a
was
famous,
excellent.
yeah, YouTube.
Yeah,
Yeah.
he's quite famous, but he had a really wonderful course on it, and that kindled my interest in that. And so that was, I don't know, 2013 or something, kind of right when everything was just exploding with convolutional neural networks. And so I was kind of observing this, very rapid increase in the interest of neural networks once again over a few years. And um, eventually, yeah, just really wanted to jump in and give it a shot and start using those myself. And so I just kind of found a way to use them mostly to learn how all of this great auto differentiation software works. This was, yeah, also really early on when it didn't work very well and was quite challenging to use. But that through that experience, I've kept with it, and now the field is, much too large to fully understand. But I really enjoy continuing to learn about it when I can. Yeah.
Yeah, you mentioned a lot of interesting points. So, if I were to summarize it in a few sentences, as far as what I understood, so during your basic physics degree, you did a few projects and you got interested in scientific instrumentation. And with microscopes, that's like sort of one area where you have control over the entire pipeline. So you know like your parameter space even within with the instrumentation. And then you also like the algorithms. You got interested in neural networks, but it was at a time where it was like, what are you doing? But you wanted to like get deep into it, and then you just found ways of doing it, and now you're just doing it. Right.
Yeah, pretty much. Yeah. Yeah, and they're at the point where there's so many different aspects for how these deep machine learning methods work that it's really challenging to keep up and fully understand how and why certain methods are making progress or outperforming or might be of interest or use. And so now I more rely on graduate students in my lab and others, friends and colleagues to point me in the right direction, I think, for a lot of these more advanced methods. But yeah, we'll see. I think it's going to continue to evolve and grow and provide interesting and new and useful features that, I personally at least will adopt into the space of microscopy to help improve, yeah, how those instruments work.
Yeah, it's interesting that you mentioned like the fundamentals, and even if the field evolves rapidly, I think it's growing in breadth, maybe not so much in depth, like in terms of like the fundamental like building blocks. And you said that you were interested in it. So that's actually, yeah, something I wanted to ask you. I was planning on asking that later on because it's sort of more technical, but like the way I understand it is that so because I also come from a physics background, and you're trying to maybe find a function which describes something, and you're sort of looking for a function which can approximate anything, so you need a universal function approximator and a new at least a real valued single layered neural network uh, is shown mathematically to do that. And then I always use the word observed universal approximation capabilities for multi-layer perceptrons or CNNs, because for real value there isn't a proof, right? So that's why we use it in physics, is what I understand. But the thing is, the fundamental unit is the neuron, and you sort of want to mimic biological intelligence. And in the 1960s, it was shown that complex valued neurons, as opposed to real valued neurons, are more functional. Recently, neuroscientists have shown that they can compute the XOR gate, which a real valued neuron can't. Optical computing supports complex valued neurons. And within optics and wave based physics, your at least in quantum mechanics, your problem is intrinsically set up in a complex valued space. So if we use a real valued neural network, we are projecting it onto a subspace which is less functional. So why not use complex valued neural networks? Is a question I've been asking, but it's so deep in the weeds that um, it's sort of I couldn't really get an answer from anyone. And even in terms of developing the software, like I think the scope to do it ab initio in Julia, as opposed to using something off the shelf like PyTorch, which as a physicist, I prefer having control over the entire pipeline. So I'm like, why do I need to use JAX and PyTorch? Why can't I just write my own neural network? I can if it's not done and if it's useful. So since you're interested in like the fundamentals, you do optics where complex numbers are so important. Do you have any thought of neural representations using complex numbers?
Yeah, a little bit. So yeah, I've experienced all of that firsthand. I guess when TensorFlow first came out, I was what like kind of a, I guess probably a pretty early user. This is in maybe 2015, 16 timeframe, and it didn't support complex numbers, but I needed them because my inputs and outputs were complex valued, or I was allowing those degrees of freedom. And so I had to code everything separately, all of the real and imaginary stuff, and do some tricks to make sure the gradients were flowing and complained a lot on forums to the developers at Google to support complex numbers. And then, yeah, lo and behold, around, I forget which year, something like a couple of years later, took a while, but 2017, 2018, maybe it started to support complex numbers. So um, yeah, I'm glad for that because for those who want to have more physical insight into, you know, um, things that aren't just text or whatever uh, pictures that are basic of cats and dogs or handwritten digits. The complex value, numbers are kind of the basis of a lot of physical work, and so supporting that is really useful. Yeah, and then I guess as for how the weights themselves, the neural network itself, the neurons themselves could, whether or not having them be complex or real. Yeah, also is an interesting question. I think it can certainly probably just enhance flexibility and add more degrees of freedom. And I'm sure folks have tried it and found different interesting things. I'm not a total expert in that space. But yeah, I guess in practice, when you're dealing with actual experimental data, trying to use neural networks to interpret or help assist with, the kind of analysis of data, the fact that neural networks provide a universal function isn't so important. What we struggle with a lot more is that the data you capture for training an algorithm, really needs to be representative of future data you might collect. Things change in an experiment, so you capture data on one day versus another, patient cohort A, and then you start to look at patient cohort B, and any little changes in that can really throw your own network right there. Problem I see that really we focus more of our attention on.
I think like you got cut off like the last few sentences, so could you please repeat that? I understood that you were saying that it's more about curating the data very carefully.
It's about curating the data very carefully, and we spend a lot of time in my lab in our research dealing with that problem of data fidelity and
Hmm.
ensuring neural networks are robust to data that might change, or that when you actually use the network might throw the neural network off a bit because it's slightly different for an unexplainable reason.
That's yeah, I think data is king for machine learning, and having good data is, yeah, it's of paramount importance. And if you don't have that, it's really hard to get any sort of insight using a ML algorithm. So that's there. So with the complex numbers, was the use of complex numbers mostly to support the hardware and the fact that all the optics relies on it, or was it more an investigation into like the basic math of how you can have a complex valued like latent space? Or yeah, so was it tailored more towards supporting the hardware because you're using optics, or was it more into like algorithm mathematical foundations?
It was the hardware. It was if you want to accurately model how a microscope works, a bright field microscope, not a fluorescence microscope, then you need to account for complex value numbers, because all objects, when you look at them under a microscope, they can absorb light, but they also can cause light to diffract and shift in phase. And that diffraction, that shifting in phase, fundamentally requires complex values to describe it. And so if you want to fully, even not even fully, if you even want to get close to accurately simulating how a microscope works, you need to work with complex values. And in those investigations we were doing, that was our central goal. And so we had to add them in.
So what are your thoughts about exploring this on the algorithmic side, like actually building out a complex value latent space, not so that like it should support hardware and it should support other wave based physics like quantum mechanics, or or be like even maybe you have a lot of motion tracking problems where you have something moving through space, and that's described using like quaternions, which are hypercomplex numbers. So I'm thinking more of like a complex valued physics informed neural network, but everything on the algorithm and math side where you have an open source package written up in Julia, or you have the theorems for like proving convergence and various architectures and things like that. And then tying it to like the neuroscience perspective of having an XOR gate being solved by a complex valued neuron. And then having it later tie into optical computing and like microscopy problems and maybe motion tracking problems where you care about hypercomplex numbers. So what are your thoughts about that exploration?
Yeah, I guess it's a trade-off. So I think yeah, making weights, right, the network itself complex valued and opening up the you know whole infrastructure to support fully complex transforms will I'm sure be more flexible and lead to new abilities and discoveries. But it comes at the cost of computational complexity. And so I just know that people are also pushing the other direction. They're saying all neural networks should just have binary weights, just ones and zeros,
Oh,
right? And those have been shown to work quite well. And they have the added benefit of not being much more computationally and efficient to compute in the sense that you no longer need to do multiplications, you just need to do additions. And so when you have that a reduction in complexity, then the benefits of the GPU effectively go away. And so you're no longer constrained to having to buy the latest and greatest sense of NVIDIA GPU, which has a certain memory limitation. You can use CPUs and be efficient and take advantage of, much larger memories. So I guess, yeah, there's trade-offs in this whole space, but I think exploring them all will is great. And I think tailoring your neural network architecture to your specific problem area is really the way to go, right? You really want to find what works best and push it and keep improving it.
but what about the fact that the electron, like most of the back propagation is running on electronics, and the electronics are not supporting complex valued arithmetic. And the electronics don't seem to be good when with LLMs we need so much compute power. So what if do you think we'll have to move to a paradigm where optical computing becomes king? And if it does, then would we actually need this complex valued stuff even, or if we go in that direction, then would this be less, would using inherently complex valued latent spaces in neural networks be less of a bottleneck if we shift to an optical computing paradigm? And do you see that happening with LLMs and everything that's going on?
Yeah, the whole optical computing thing I think is also very interesting. It's my first job after I was an undergrad. I went to work at a company that doing research where my boss, his name is Ravi Athali, did a PhD in optical computing in the 1970s. And I obviously learned a lot about it from him, but it's been around a long time, right? And I think it's fascinating. I think it's made inroads in certain areas and has been, you know, bested by electronic computing in many other areas. And it's really hard to try to develop a technology that is attempting to scale with Moore's law because you essentially have to keep up with electronics, right? So there's a lot of challenges, I think, in terms of competing with electronic computing, right? And also, light, it's great for certain applications of sending information, right? It's very information rich when you do get it into a fiber, or it can be. But it requires a lot of space. And a former advisor of mine would say photons are really fat,
Huh.
right? They have to sit within a half micron area effectively. Electrons are much, much skinnier, right? You can go down to angstroms. So it's many orders of magnitude more space is required. And so that's another challenge with optical computing. So yeah, we'll see. But I think I see this evolving in a way that things will become tailored for specific applications, right? So machine learning is going to pervade a lot of spaces and applications, and certain applications are constrained in different ways and require, you know, maybe optical computing to assist, whereas others don't at all, and will be fine with, the power of regular electron-based computers for years to come, probably.
So things need to be like sort of tailored to the application.
So definitely, well, that's always the best, right? If you have that ability, then you can always improve your performance, right, compared to what is kind of standard.
Mhm. So was like your course, the one you designed, like ML and optics, was this something which came out of like tailoring towards application, like tailoring? Was it something like I want to tailor ML for optics, but in a broad sense, and then develop the course? What was the like motivation behind developing that course, and when were the seeds sown, like in your head, like, oh, I'm going to do this course? What's the story?
Yeah, that's a good question. I guess most professors starting off, at least here at Duke, I think at other universities as well, are usually given the chance to design a new course. And so I was, and uh, I was working on that topic of using machine learning to kind of model imaging systems and optics, and then optimizing certain aspects of imaging systems and how optical platforms or measurement systems can work. And I just had a lot of material and it just was fortuitous, I guess. It was a graduate student course, and the graduate student courses I enjoyed the most when I was a student were ones where you could do a project that you could really kind of dig into and hopefully connect to some of your research that you're doing, in a lab. And I tried to make the course accommodate that. And I saw a lot of ways in which machine learning and the ability to design, co-design, or co-optimize how images or certain properties of images are acquired, or how they're analyzed, could really help a lot of different groups in general, especially here at Duke, where there's people working with all sorts of imaging instruments at the clinic with MRI and CT data, and then in laboratories, right, with electron microscopes or optical microscopes or regular cameras or whatever it might be.
Yeah, that's a fascinating story. So what are the challenges you faced when were designing it, and once you started delivering it? I'm sure you there would have been things popping up which you probably didn't think of, or like you were maybe biased towards one thing and you found out that the opposite thing is true, or stuff like that. So were there challenges popping up as you sort of went through with the course?
Yeah, there's always challenges with every course I've learned. And it changes every year, even
Mm.
if it's a very similar course, right? The students and the timing and everything is different. So, yeah, I think a lot of the challenges we faced were, allowing or encouraging the students to use the latest and greatest software tools when they were rapidly under development. And so keeping up with, the developments in these platforms like PyTorch and TensorFlow, allowing
Right.
students to get access to a significant amount of compute power without a large cost, making sure they all understood how to deploy and work with code at kind of a funny scale, right, where you're generally running in the cloud, was also challenging. So we worked through a lot of that. It took some time, but it continues to pop up as a challenge because software always changes, and if you want to keep up with the whatever's working the best, you have to change.
Yeah, I think that sort of organically brings me to my next question or something that I've been thinking about. So I am really interested in teaching a course. I think we did discuss this in earlier emails for like physics informed machine learning or scientific machine learning. And at that time, I had started using PyTorch, but I picked up JAX. And I was told at my university that I don't hold a PhD, so I can't teach a full course because whatever politics. So with the startup, they're like, yeah, we don't care. If you're good enough, you can teach. So then I started developing these lectures, and I think I sent you the link to the first one. And the people I'm collaborating with, they're really biased toward Julia, partly because they're MIT grads, and I don't need to tell you about that. And I'd started learning Jackson, and I thought it's a good tool. So like I had the second lecture where it was just focused on if you're a physics or an engineering student and you don't know much about writing code, can we use some physics problems to introduce automatic differentiation, automatic vectorization, object oriented programming, walk you through like just the basics, starting from like slicing arrays in NumPy to autodiff and auto like VMAP in JAX, and then the OOPs, and then combine everything and sort of just have one comprehensive like lecture on that, because then you sort of know why and how you're using these tools when you see like a problem from mechanics or very basic physics being solved using these things. So I don't know if that's a good way to help students get used to like a platform like JAX, because they could be scared, oh, it's what is this JAX thing? And then you have suddenly have a neural network with loss functions and this and that and so much code with the physics models. So I don't know if that can be helpful. So I did put out a lecture like that, but I don't know if that's helpful. Any thoughts on that?
Uh, yeah, I think you just have to try a lot of different things and figure out a sequence of how you want to introduce that material that works with people who are unfamiliar with it. Yeah, I think there's lots of ways to instruct people, especially in this space. And it's, in my experience, pretty challenging to determine an optimal way without actually just kind of trying it and sharing what you have with other people. Because, yeah, sometimes something seems really complicated in TensorFlow or PyJax or whatever it is, and people actually can pick it up pretty quickly compared to some more simple, what might seem like a simpler concept. People can really struggle understanding it when they're trying to implement it. So yeah, it's really something you just have to experiment with, I think. But I was going to ask, do you know Srinivas Taraga? Do you know him or no? Have you heard of chromatics?
No.
Chromatics. Okay. Yeah. So there's a researcher friend. He's at Howard Hughes Medical Institute, called the place called Janelia Farm, which you may not have heard of. It's very biology focused. It's this really, research institute with a capital R type place that studies all sorts of biology. he 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 is really a big fan of JAX. He also is interested in microscopes, designing them, and he and his team, including a couple students in my lab, have been working on like an open source package in JAX called Chromatics, which supports like wave operations and propagating light and modeling different microscope elements and things like that. So yeah, you might check that out. I think they're always looking for folks to join the team and help with the development. They host hackathons. in the past, I know they've invited people to Genelia to kind of work together for a few days or a week or whatever. So you might like that.
That sounds a lot of fun. I'll chromatics and Genelia, right?
Yeah, if you just email me whatever, I'll remember to respond. I could send you links.
Yeah, I think that would be a lot of fun to check out.
Sure.
So, what's maybe the one piece of advice you would give to someone building a course like this out of the discussions we've had and your experiences in the past?
Yeah. Of course, like where you're introducing machine learning for physics type
Yeah,
modeling
not
or physics
optics,
informed learning.
physics,
Yeah,
physics
sure.
and engineering, right?
Absolutely. Yeah, I think what are some good pieces of advice? It has to be a lab-based course where the lab component is learning how to program in whatever language you're choosing. I think that's unavoidable because a lot of the students won't come in with that experience. And in my experience, teaching code is, one piece of the puzzle. It's less effective when you're lecturing about how to do code versus actively instructing and doing active learning where students are actually coding and then you're giving small problems and working together as a team to come up with, which is the lab. Um, and then another piece of advice is, yeah, having templated coding exercises really helps because students tend to, everyone tends to get stuck on, kind of complexities of code that probably aren't so central to the learning process. They just are, nuances of somehow a function is called or something that you kind of get annoyed with, or, hopefully don't get too annoyed with, but maybe just are really puzzling with that isn't the best place to spend your time when you're trying to learn a new concept. And so filling those in, having that populated with code, right? And then leaving the key parts that are the most informative for the topic at hand for students to fill in is, in my experience, a great way to teach those concepts.
Yeah,
Um,
yeah,
yeah,
there's
then making a project based. It's really important, I think, having it be connected to things that are meaningful and have it be not just one course, but or one lecture, but kind of building on concepts to create something larger with more interconnected ideas is great. So that's another thing I think is very helpful.
Yeah, there are a lot of like nuances like using certain functions, and I think there was one thing where I had to like look at the memory locations once. There's some weird thing, and I didn't realize that would be the biggest problem. I was stuck on it, and then once I overcame that when I was like creating this video lecture where there were Jupiter cells and I was walking people through it, I realized that I should talk about that because it's like those nuances where people are going to get stuck and never know what's happening. And then I take that nuance and like maybe use Chat GPT to be like, can you give me like a super simple example where this can happen so that a 15-year-old kid can understand and he'll do something, he'll make mistakes, I'll take it, tweak it, and then have that as an
Mm-hmm.
example. And that seemed to have worked because the lectures are on YouTube, so I'm not interacting with people, but people sometimes watch it and then send me a message on like LinkedIn or like email me saying they liked it or they didn't understand this. So having it
Yeah.
more interactive, maybe in person, if there's a way to do that, and then helping them actually do the coding is I think yeah important. Um,
Yeah. Yeah.
and I think like going back to your machine learning beginnings, you said you got into it when it was like relatively new and people were like skeptical about neural networks. So what was like the one like what was the turning point or what was that exact like thing where you're like, oh, what made you really like look into neural networks the very first time? Do you remember that?
Um, I mean, I knew about basic neural networks for, yeah, the concepts of them, right, that go back to the 80s and early 90s, at least when there was a lot of excitement about them. I just knew about them in general from probably different courses or just my own reading. Um, for a while, much before, let's say, 2014, 15 timeframe. And then I took that machine learning course, which again wasn't about convolutional neural networks. It was just about neural networks at Caltech. And so what really changed was, yeah, the convolutional neural network. That's what really, I guess, piqued my interest from simply learning about the material to using it and applying it because it worked really well. And so, yeah, the convolutional neural network, that simple 5 layer, design that was, I think the first paper about that was in 2012. Took a couple of years to trickle out and have people using it. But I just was kind of aware of it. And then I actually had a friend who was at the Media Lab still at the time, who was using them and just said, yeah, they work really great, right? These are significantly better than any other method that we've tried before. That kind of tipped me over to say, okay, well, now I really want to learn about how do you use these, right? How do you actually implement them with the software that's required to get them to be trained efficiently, right? And that software was similarly being rapidly developed by, luckily for free, by free for all of us, by people at Google and Facebook. It was just an opportune time to kind of adopt that and get going.
So you would say like early adoption plus just curiosity and interest, and that just organically led to you doing it. It wasn't in like an external aha moment. It was just like just happened sort of.
Well, the aha moment for me was, well, I didn't want to just, download images and classify them. I'm not excited about that. The aha moment for me was, yeah, thinking about how you could just, make certain properties of the image itself, the imaging process itself, right? Learnable weights, and then jointly optimize those, right? So being able to design parts of the camera, right? The color filters you're using over the pixels, or the way in which light is shown on the object, things like that. And so I got really interested in that and was working on it for microscope images, and then was introduced to a paper by someone named Ayan Chakrabarty, who had done a very similar idea for designing color filters on a camera. And I was just even more motivated after that. I said, wow, this actually works. This is great. Let's see how it works in a microscope, and what we can learn from these methods there. And so it kind of was a slow process, I guess, of seeing some exciting technology, really wanting to try it and learn how to use it, having an idea of something new you could do with it, and then being motivated by seeing others who kind of successfully took the same idea and pushed it forward. Um, and yeah, continuing that, and then using that to teach other younger students, right, in my lab here at Duke, to then have them have their own projects and their own ideas and their own directions of investigation, was kind of the lifeline, the whatever trajectory of those events.
So is was the idea of physical layers born out of all of this? Like have sort of the not just cats and dogs, but the imaging merge into like the ML pipeline? Like is that what?
Exactly. Yes. Yep. That's exactly it. So you can kind of put them seamlessly together, right? When you're putting in images of cats and dogs already to classify them, there's nothing preventing you from then modeling further upstream. How were those images captured? How did the light pass through the lens or reflect off those cats and dogs? You can go ahead and model that in your neural network pipeline, and optimize components of that, so that after training, you not only have a good way of classifying images of cats and dogs, but also could potentially design a camera that can better classify cats and dogs, right? Or design a way to illuminate the world to better classify different things. So the examples we focused on were really in the microscope and improving the design of microscopes to better classify diseases like malaria, or even COVID-19, things like that were something that we've worked on in the past and we're excited about. Yeah.
And so is the when you have these physical layers, is actual computation optical at that point for those layers where it's the actual, is it like hybrid optoelectronic network, or is it a network on the computer where you're modeling that with optical weights, fixed weights for point spread functions, or yeah, is it purely, wouldn't be purely optical, right? Is it hybrid or is it on the computer?
It really depends, but certain things we can get optimize a first part that was purely optical, right? And so that would have to do with how the pictures were captured, how the camera is designed. And then a second part is the digital part. So once the pictures are captured, a specific neural network would then classify those. Yeah. So that's generally how we approach the problem. But yeah, now there's many ways to slice and dice that particular problem. Yeah.
Oh, and that's why I guess I read through your course description. You say that we won't just be classifying cats and dogs, and that's not the sort of project you should do. I think you make that clear in the course
Yes.
description, right?
Yeah, exactly. Yeah, as an engineering course, I really try to focus on not just adopting tools, but knowing how the tools work and trying to, yeah, learn about the design space and the various criteria needed to meet certain objectives as an engineer, and pushing that critical thinking forward is important. So I think that's always a good goal in a course that you're designing as well.
Yeah, I sort of like that, and that's sort of the advice I've heard, which I've adopted. That you sort of want to solve a problem from your domain and then use ML rather than doing this Coursera cat dog classification where you don't really feel like you learn much because the math is really easy for like someone coming from physics or engineering, and then if you know enough coding you can do it, but you feel like you haven't really gotten the point. So I guess for me, like if I have to get the point, I'll have to take a pure math course where I derive all the approximation theorems or solve a physics problem where it's like you actually have to solve the problem. So I guess both those approaches I think are like great. But do you have any tying into that? Do you have any advice for maybe physics and engineering students who want to break into machine learning and data science, and they're doing it maybe it's a uh, it's curiosity driven, but it's also there's also this thing of careers and having jobs where there's a lot of jobs in this space, so people might want to transition for those reasons. So it might be a multi-pronged sort of thought process where they're like, yeah, I'm curious about this, but there are jobs in this area and research opportunities. So if someone's coming into machine learning and data science from that perspective, but maybe they're physics or pure science or engineering and know a bit of coding, what's your advice for them?
Yeah, good question. I have to go in just a couple minutes or
Okay.
one more minute. But yeah, I guess my advice would be to really try to learn the basics, right? Really try to start kind of from early first steps to make sure you understand, how everything works. Because if you just learn whatever the latest and greatest tools are and you just adopt them, right, those will change. They're changing all the time, very rapidly. And so, it's hard to make progress in a meaningful way in your career if you just quickly learn how to use tools, um, because they're going to change and you'll have to quickly learn how to use this ones and you won't be very good at using them if you're just quickly learning everything, as opposed to really trying to figure out kind of the basics and then any new tool that comes out in the future, you'll be able to have a better understanding, at least a little bit of how it's operating and be able to, adopt them more effectively. Um, and so, yeah, I would suggest that, and I would suggest, yeah, be uh, to use them, right, for kind of take try to write your own methods, I guess, or don't just download code, but try to kind of work towards being able to write your own very simple code. Because if you get to that point, then you can be the designer. You're in charge of everything, right? And you can change things, and they might break, but you'll know how to fix them. And that's a real understanding, right? As opposed to just downloading something and trying it. uh Maybe it'll work, maybe it won't. You won't necessarily know why or how. And you won't be able to tweak and change and alter things um while maintaining that understanding.
Yeah, I think that was like really nice advice, and I'm sort
Sure.
of, yeah, along that direction. I'm planning on coding up like a complex valued neural networks from scratch in Julia using this paper. But I guess like following up, I'll send you an email, and I forgot the name of the team you spoke about. We should.
Sure.
w-
Yeah,
w-
I'm happy to send you their information.
Yeah, and so we should sort of follow up with that. And yeah, with that, I guess like thanks a lot. It was great talking to you. I learned a
Yeah,
lot, and I hope the people who watch this on YouTube will also learn a lot. And
great.
yeah, we'll stay in touch, and I'll follow up with email.
Okay,
Yeah,
thanks. Have a
yeah,
good one.
yeah. You too.
Okay,
Bye. Thank you.
bye bye.